Welcome to Honors Physics. This is our kinematics equation proof video. So the first equation, some of you have seen this before, comes from when we look at an object that's moving with a constant acceleration. And if we were to graph this object, it might look something like this on an acceleration versus time graph. We would have a line going straight across. Now let's just say that the value of that acceleration is the symbol a, and that I'm looking for how much the velocity changes from time t initial to time t final. Now we know that in general the change in velocity from a graph of acceleration versus time is equal to the area under the acceleration versus time graph. And so if we were to take a look at that, that would be, if we were looking for the change in velocity from t initial until t final, we would be looking for the amount of area enclosed by this shape right here, this rectangle, which is this green shaded area. So this green shaded area is a rectangle, which means its area is given in general by base times height. So our base here is t final minus t initial, and the height here we see is a. So in general, the area is equal to t final minus t initial times a. And as we see t final minus t initial, we're just going to call that t, where t is now going to represent just some general time period. Time period. So say, for instance, this occurs from 2 seconds until 7 seconds. You, rather than saying that it's 7 minus 2, you can just plug in a t of 5, right? So you would have 5 seconds that this was occurring. So that means that we have t times a is equal to our area. Now, how does that help us? Well, if we know that our area is equal to the change in velocity that we see up here, then we can say now that our change in velocity, delta v, is equal to a times t. And as we mentioned yesterday in class, the delta v doesn't give us a whole lot of information about the final velocity. The only way that we can find information about the final velocity is by knowing the initial velocity. But the nice thing for us is that the definition of a delta of something, delta v, for instance, is v final minus v initial. So when I plug that in here, I end up with v final minus v initial is equal to a times t. And if I wanted to just rearrange this equation and solve it for final velocity, I have v final equals what? V initial comes to the other side plus acceleration times time. And this red equation here is the first of your 4 kinematics equations. That in general, when we are looking to find the final velocity of an accelerated object, we can find it by taking its initial velocity and adding to it the acceleration multiplied by the time that it's actually accelerating. A similar thing occurs when we look at the displacement of an object with constant velocity. So let's take a look. If we have an object that's going with constant velocity, that means it's a horizontal line. And again, we know that this statement is true, that the, not delta v this time, but delta x, the displacement, is going to be equal to the area under the velocity versus time graph. So again, if we take a look, we're looking from some t initial here to some t final down here. This would mean that we are looking for the amount of area that's enclosed in between these two bounds here. And so if we shaded this in, right, we're looking for the size of that area. Again, this is a rectangle, so our area is equal to base times height. In this case, our base here is again t final minus t initial, and it is important to have the parentheses here. And our height here, now this is some velocity, so we're going to call this some velocity v, and we're going to call this v average. Okay, v average. So this would be multiplied by v average. And that's going to be important for a little bit later on. Again, we can collapse this t final minus t initial down to just a t, because that represents how long this object was moving, or how long we care about it moving. So again, if this was 2 and this was 7, the t would be equal to 5. And we're going to multiply that by our v average again. And then again, we connect these two pieces, that x is, delta x is equal to the area underneath, so we come down here, and we end up seeing that delta x is equal to v average times time. And this is kind of similar to an equation that you've seen before, which is distance equals rate times time. That's what's happening here. Distance is our displacement, rate is our average velocity, and time is, well, time. Again, we can see that because delta x is equal to x final minus x initial, that we can plug this in over here and end up with x final minus x initial equals v average times time, or that x final equals v average, let's rearrange it just a little, x initial plus v average times time. And we're going to highlight this a little bit. This is our second of our kinematics equations, equation number 2. So let's start a page with these equations here. We'll add this to the very end. So far, we've got equation 1 is that velocity final equals velocity initial plus acceleration times time. We've also got that x final is equal to x initial plus velocity average times time. Now, the reason that we didn't have an a average up here is because we won't ever be changing our acceleration as we go through a problem. Velocity may be changing, but the acceleration will not ever change. We'll have constant acceleration. Now we get into something a little bit trickier, which is displacement with constant acceleration. Now, if we were to look at a displacement versus time graph of an object going with constant acceleration, because the slope of the graph represents the velocity, constant acceleration means that we're having an ever-increasing velocity. So an object with constant acceleration might look something like this, where it's going to be speeding up and speeding up. It could also look something like this, where it started off and it's going much, much slower. We could also have something where it started off very fast and then slowed down. Or we could have something where it started off very fast in the negative direction and then also slowed down. Okay, so we've got kind of these 4 different possibilities for what the displacement graph looks like. But if we took a look at what the acceleration graph looks like, we have acceleration and time here. We have constant acceleration. So again, we're just going to have a horizontal line going across like that. And we're going to call this acceleration A. Now, if we took this acceleration graph and we converted it to a velocity graph, velocity versus time, up here we see that A is not equal to 0. We have a non-zero acceleration up here. So what does that mean down here? Go ahead and pause the video and think about what that means for the slope of this graph down here. Hopefully you translated this acceleration being non-zero into the fact that the slope of the velocity graph is non-zero. Now, the slope of the velocity graph being non-zero means that we have not a straight line, but we have a diagonal line. We have a diagonal line. And for interest's sake, we're going to say what happens if we start off at some initial velocity and have a diagonal line that goes up like this. So we'll say that the slope of this line is equal to acceleration. Slope is equal to A. And let's figure out how far the object traveled from time t initial 2 times T final. So go ahead and pause the video. See if you can figure out an expression for that area. And welcome back. We should be looking at the following area here. We've got the lower bound and the upper bound. Now, there's two ways that we can take a look at this area. The first is by saying that it is a trapezoid. Trapezoid. And the area of a trapezoid is given by 1/2 the base times, in this case, height 1 plus height 2. And we can think of it like this. The 1/2 actually goes with the height 1 plus height 2 because we've got two different heights here, and we're looking for the average between them. If we had an average line going between them, then we could just make this a rectangle and it would be base times height. So the 1/2 height 1 plus height 2 means this is our height 1 and this is our height 2. So let's call this one V initial right here, V0, right? Because we've got T0 and V0. And we'll call this one up here V final, right? Because it's T final. And so what's our area? Well, the area here, this whole big giant thing, we said was 1/2 the base, and the base is T final minus T initial. And our heights are V final plus V initial. And so we've got 1/2 T times V final plus V initial. Okay, so this looks pretty similar. In fact, from here we can say 1/2 V final plus V initial is actually V average. And so we can get our second kinematics equation just from this. But more interesting is we know that V final is equal to V initial plus acceleration times time. And so if I take this and I plug it in right here, I'm going to get the following. 1/2 VO plus AT plus VO times T. And if I expand this, I get 1/2, or combine and expand, 2VO plus AT times T, or VO times T plus 1/2 AT squared. And this is our area. Now, what does this area represent? It's the area underneath the velocity curve, so this represents our delta x. And so just like we did before, we can now say that this is x final minus x initial, and we can come up with our third kinematics equation, which is that x final equals x initial plus all of this stuff up here, VOT plus 1/2 AT squared. So we're finally on to our last equation here, and to find this one we actually can't really use a graph, or it's not quite as intuitive to use a graph here, so we're going to rearrange some of our previous equations. We're going to start with the delta x equation equaling V average times time, and realize that, well, we can keep the delta x. That V average is, for an object with constant acceleration, half of V initial plus V final. Now, we also know that for an object with constant acceleration, the final velocity, delta V, delta V, is equal to acceleration times time. And equation number 4 is unique because it has no time component to it. And so because it has no time component, we want to get rid of the time pieces. So if I solve this equation for time and solve this equation, or plug it into this equation here, we're going to get rid of our time. So time is equal to delta V divided by A. And when I take that, I end up 1/2 V initial plus V final times delta V over A But remember again, delta V is equal to V final minus V initial. So we get 1/2 V initial plus V final times V final minus V initial, all over acceleration. And if you remember your difference of squares, this is equal to 1/2 V final squared minus V initial squared over A. And this is delta x. So now, if I rearrange this equation, I can bring the 2 down here, and I can rearrange this to say that 2a times delta x is equal to v final squared minus v initial squared. And the typical way that we report this equation is like this: vf squared equals vo squared plus 2a times delta x. And that is our fourth equation. So then we can see that we have now 4 equations. We've got these two, then we've got x final equals x initial plus VOT plus 1/2 AT squared, and our final one, that V final squared equals V initial squared plus 2a times delta x. And these are sometimes known as the big 4 kinematics equations. Each of them is useful in some particular instance. Some are more useful than others in other instances, and we will learn how to use them.